Okay, state space approach or state space methodology. Using the state space approach, we represent physical systems with first order differential equation. Okay, so now it means what state space approach is to represent your system, your physical system, with a first order differential equation. So you will never see x square or x double dot. X, always you use x dot. Okay, first order, always first order differential equation. So you don't see double dot, for example, as a second order. This representation is used in modern control theory as opposed to classical control, where we use transfer function, body plot, root locus. All of those, transfer function, body plot, and root locus, all of those are based on classical control theory. In modern control theory, we prefer to use state space representation, and that's how the state space representation is about. You see, it is first order differential equations. So here it's a vector with many first order equations, and this representation, it's directly an indication of a linear time invariant system. As a transfer function, it's for linear system. We are doing linear control. So if you have a non-linear system, you need to linearize it and work about the operating point. You cannot go far away from the operating point. Later, maybe at the end of the chapter, I may show you some way how to use the linear control theory to control non-linear system. There is a way we call it gain scheduling. If you want to search for gain scheduling, is a way to control non-linear system using linear techniques. But in general, we are focusing in this course on linear system only. So your system should be linear, or you need to linearize around an operating point. So then transfer function, it's a linear representation. State space representation, it's a linear system. It represents a linear system where x is from x1 to xn. So now pay attention to the dimension. Like x, it has a dimension of n. Y, it has a dimension of m. Could have n and m same dimension? Yes, you could have n equal m. So then, and x is the state vector. This is very important to note. X is the state vector. Okay, don't get confused. X is not an input. X is your state. Okay. However, u is your input vector. U is your input vector. Okay, u is your input vector. And y is your output vector. So those are your input and output. So in MATLAB, when you put state space representation, you have u and you have y. Okay, I will use this notation to represent a vector. Means you have u1 up to ur, so like this. Here in our PDF, we are using bold to represent a vector. See this bold, it's a vector. To differentiate between scalar and a vector, we use bold. You see bold. Myself, I will use an arrow. So then u1 up to ur, and y is y1 up to ym. And here I have x1, I have my state x1 to xn. Okay, that's your state x. Okay, so these are the vector. You have three vector, x, y, and u. That's it. And you have four matrix, A, B, C, D. A, we call it state matrix. A is the state matrix because this is your state variable. A is the state matrix, and it is n by n by n matrix. So the state matrix is n by n matrix. x1 up to xn and x1 up to xn. So it's always a square matrix. Okay, the dimension of it depends on the dimension of the state. If you have two state, so it is 2 by 2 matrix. Usually, inherently, maybe most of the time you don't know the states unless if you are building your system itself, yourself. You will get practice it more and more. B, so what's B is the input matrix. We call it the input matrix because it's connected to you. So D we don't call it input matrix even if it's connected to you. Okay, B is what we call the input matrix. Right, this is the state matrix, this is the input matrix, and it is n by r. N x1 up to xn and u1 up to ur. So here you have u, here you have x, and here you have x, so n by n makes sense. Here you have x, and here you have r. You have r dimension for, so then it is n by r matrix. You could not forget it. Once you put bu, so you know n and r. C it should be m because y1 up to ym and x1 up to xn, so it should be m by n matrix. And C we call it the output matrix. It's nice and good to remember the names of them. And D it should be m by r, right? So y1 up to ym and u1 up to ur, so it is m by r matrix. And it's nice to know that which we call it direct transmission matrix. Okay, D we call it direct transmission matrix. It's a direct transmission from the input to the output. That's it. It has a name, it has a meaning actually. And C is the output matrix. C basically, physically speaking, it represents actually more the sensor dynamics and so on. It's the dynamics at the output. And B, it represents more the actuator dynamics. If you are including all of this in your system. Okay, so to change B, maybe you change your actuators and then B will change. Change your sensors, how the way you are measuring your output, and maybe the C matrix will change. Okay, A is the state related to the system, the plant itself. Okay, so yeah, that's it about dimension. We spent some time, but it's very important to understand them.